Welcome to the third day of Summer General Physics. In this sixth video, we'll be taking a look at some examples of parabolic motion problems. So this first example has to do with the video you just watched, with the kayak going over the waterfall. So this problem statement includes some more information about that venture. So the problem states that a kayak goes over PHYS Falls, which is 186 feet tall, at a point where the current is 10 feet per second. How far from the base of the cliff does the kayak hit the river? So we should start this problem, as usual, by drawing a picture and labeling some of the quantities involved. So let's say that this is our cliff, and there's water below the cliff, and of course the waterfall is going from the top of the cliff to the bottom. The cliff is 186 feet tall, and the kayak with his paddle in one piece at the top is poised to go over the waterfall. So the kayak's trajectory will look something like this. It's kind of a half parabola. And the thing we want to know is, what is the displacement in the x direction? How far from the base of the cliff does the kayak hit the water? We also know that initially the kayak is traveling along with the river, which before it reaches the edge of the cliff is going in the forward direction with a speed of 10 feet per second. Okay, so let's start solving this problem. Now, the first step when dealing with a parabolic motion problem is typically to split the initial velocity up into x and y components. In this case, it's pretty simple, because before the kayak starts falling, it is going in the forward direction, it's going in the positive x direction. Therefore, its initial velocity in the x direction, v naught x, is 10 feet per second. And its initial velocity in the y direction is 0, because all of its motion is in the positive x direction. Now we should take that 10 feet per second and change it into meters per second, because of course when we address the motion in the y direction, the motion in the y direction is free fall. We'll want to use g as 9.8 meters per second squared, so in order to make the units work out, we'll have to do things in terms of meters. So I can do a unit conversion on my 10 feet per second. I know that there are 3.281 feet in 1 meter. And that means in the x direction, my initial velocity is 3.05 meters per second, and nothing in the y direction. So then I can write down my equations of motion. In the x direction, there's no force acting on the kayak. The kayak is in parabolic motion, and so the velocity in the x direction never changes. So since I have constant velocity in the x direction, I can write down that the displacement in the x direction is equal to the initial velocity in the x direction times time. Okay, so I see that I have the initial velocity in the x direction, and I need to find the displacement in the x direction, but I don't know anything about the time. So it must be that I'll be able to find how much time it takes for the kayak to go along its path from the top to the bottom of the cliff by analyzing the motion in the y direction. So I should make a list then, since in the y direction I have free fall motion, I should make a list of the knowns. So what are the things I know about the motion in the y direction? Well, I know the initial velocity in the y direction is 0. and I know how far the kayak travels in the y direction. So my delta y is going to be equal to negative, because the kayak is moving downward in the y direction, 186 feet. And once again, I should change that from feet into meters. So there are 3.281 feet equal to 1 meter. And so my change in position in the y direction is going to be 56.7 meters. So I have that, I have my change in y, and that looks like that's about it for the information I have in the y direction. And then my unknown, the thing I want to find in the y direction, is time, because if I can find the time, I can put it into my equation for the x direction motion and find my delta x. So I should take a look at my my freefall equations to analyze the motion in the y direction. And I think looking at those and seeing how I have information about the initial velocity in the y direction, the displacement in the y direction, and the fact that I want to find time, the best one to use would be the delta y is equal to the initial velocity, and this is in the y direction, time minus 1/2 gt squared. So looking more closely at this, the thing I want to find is time, but I know that my initial velocity in the y direction is 0. So 0 times any number is 0, so this part of the equation is going to be 0, which will make the math a little bit easier. So now I can see that delta y is equal to minus 1/2 gt squared, and I want to solve for time. So I'll multiply both sides of this equation by 2. Actually, I'll multiply by minus 2, because that way I can get rid of the minus sign on this side, and then that will cancel with 1/2, and then divide both sides by g, which gets rid of the g here, and then the final step is to take the square root of both sides. So time then is going to be the square root of minus 2 delta y divided by g. So then plugging in numbers, I have that time is equal to minus 2. My delta y is, oh, I forgot the negative sign here. So if I convert minus 186 feet, I should get minus 56.7 meters. So my delta y is minus 56.7 meters. And then g is always positive 9.8 meters per second squared, because I took care of the fact that the acceleration was in the negative direction by the minus sign here. So g is 9.8. And then if I plug that into my calculator, I will get a time of 3.4 seconds. All right, so now I know the time that it takes for the kayak to make its trip from the top to the bottom of the cliff. And so the last step would be to plug that time into my equation for the x direction motion, so that I can know the distance from the base of the cliff to where the kayak lands. So my delta x will be the initial velocity in the x direction, which was 3.05 meters per second, times the 3.4 seconds, and that's going to give me a distance in the x direction of 10.4 meters. So that would be the answer to this problem. The kayak traveled 10.4 meters in the x direction as it was falling, and so that's how far from the base of the cliff the kayak will hit the water. All right, so let's take a look at this second example. So in this problem, a golfer hits a ball with an initial speed of 30 meters per second at an angle of 30 degrees above the horizontal. The ball lands on a green 5 meters above the level where the ball was struck, and I want to know two things. How long was the ball in the air, and then how far did the ball travel in the horizontal direction? All right, so let's draw a picture of this problem. So in this problem, I'm hitting a golf ball, and the golf ball takes off with an initial velocity of 30 meters per second. And it makes an angle of 30 degrees with respect to the horizontal. So then the golf ball travels through the air and it finally lands on a green. So here's my green. Hopefully that's where the hole is. And my green is, and where the golf ball lands is at a height that's 5 meters above the level where the ball was struck. So that's the information I have for my problem, and I need to figure out how long was the ball in the air, and then also what was the horizontal distance that the ball traveled. All right, so as before, the first step is to split the velocity up into x and y components. And this is actually going to take a bit of work, unlike the last problem, because I do have some of the initial velocity going in the x and some in the y direction. So if I'm calculating the initial velocity in the x direction, I would take the initial velocity, 30 meters per second, times the cosine, since this is the x component, times the cosine of 30 degrees. So the initial velocity in the x direction would be 26 meters per second. And in the y direction, that would be 30 meters per second times the sine of 30 degrees, which would give me 15 meters per second. All right, so now I need to consider the equations of motion in the x and in the y directions. So in the x direction, I know that I travel at a constant speed, always, in the x direction. So the displacement in the x direction is going to be equal to the velocity, the initial velocity in the x direction, which never changes, the x direction velocity remains the same, times the amount of time that the ball is in the air. Then in the y direction, I should write down a list of the things that I know. So my knowns for the y direction, where I have free fall because the only force acting in the y direction is gravity, I know that the initial velocity in the y direction is 15 meters per second. I also know my delta y, because I know the difference between where the ball ends up and where the ball starts out. So delta y is the final height minus the initial height. So if I set the place where the ball is struck, if I set that height as y equals 0, then the final height is 5 meters, the initial height is 0, so final minus initial would be 5 meters. Another way of thinking about this is that the ball ends up 5 meters above where it started. So overall the ball went upward, and so the delta y is positive 5 meters. So then, is there any other information I know about the y direction motion? No, I think that's it. And the unknown, the thing I want to find, the thing the problem is asking for, is time. Because the first part says, how long is the ball in the air? That's the first question I have to ask, so I want to know time. And then also, if I have time, I can plug it into this equation, since I have the initial velocity in the x direction, and find how far the ball traveled in the x direction. So let's try to solve for time. So if I look at my free fall equations, and I look for one that has the initial velocity, the displacement, and time, I think probably the best one, the one that I would want to use, is once again delta y is equal to the initial velocity in the y direction times time minus 1/2 gt squared. All right, so I need to rearrange this equation to solve for time. But this is going to be a little more tricky than the last problem we were looking at, because in the last problem, the initial velocity in the y direction was 0, so this term went away. But now it's not 0, it's 15 meters per second, so I have some number multiplied by time, I have some number multiplied by time squared, and I have another number here, also not 0, so this looks like I'm headed towards a quadratic equation. I want to solve for time, and I have a t squared term, a t term, and a term that doesn't have t in it. So I need to use the quadratic equation to solve for t. So my next step will be to rearrange this equation so that I can apply my quadratic formula. So I think what I'll do, in order that I get a positive number multiplying t squared, which isn't necessary, I find it just a little easier to work with, is to move these two terms to the other side of the equation. So if I do that, I would get positive 1/2 gt squared minus v naught yt plus delta y is equal to 0. So then if I think about my quadratic formula, the thing that multiplies the squared term, that's my a. The thing that multiplies the linear term is my b. And then the thing that gets tacked on at the end, that's my c for the quadratic formula. So then we can write down a solution for t. So time is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. So the only thing that remains now is to plug in numbers. My initial velocity in the y direction was 15 plus or minus the square root of 15 squared minus 4, and I have a 1/2. G is 9.8 positive. My delta y is 5 meters all over, well, the 2 and the 1/2 cancel, so in the denominator I would have 9.8 meters per second squared. Okay, so if I plug all that into my calculator, because of the plus and minus, I'll get two solutions. One of the solutions is 0.4 seconds, and the other solution is 2.7 seconds. So I get two solutions. Both of them are positive, which is what I would expect. So which solution do I choose? And does it make sense that I have two solutions for time? Well, if I look at my picture and think about what I was solving for, I was solving for when the ball was at 5 meters above where it was struck. And I can see that indeed there are two places where the ball is 5 meters above where it was struck. Here, where it lands, but also here, where it's still going up. So the 0.4 solution must correspond to this first time that the ball was at 5 meters when it was still traveling upward, and the 2.7 seconds must be when the ball was finally landing. So it's the 2.7 second solution that I would want to select. I can see from the picture that I drew, it makes sense that I have two solutions. But in the first one, the ball was still going upward, and when it lands, the ball is moving downward, and so that would be the later second solution that I'd want to select. Okay, so now that I have the amount of time that the ball was in the air, it will be easy to figure out how far in the horizontal direction the ball traveled. So just using that expression for the horizontal motion, the displacement in the x direction is 26 meters per second. The velocity in the x direction times the amount of time, 2.7 seconds. And so for the distance in the x direction, I get 70.2 meters. So that would be the distance that the ball would travel in the x direction from where it was struck till where it lands. So here are some questions for you. Let's suppose that you are carrying a ball and you're running at a constant speed and you want to throw the ball and catch it when it comes back down. How should you throw the ball? Should you throw the ball at an angle of 45 degrees above the direction you're running in and maintain that constant speed? Should you throw the ball straight up in the air and slow down? Or should you throw the ball straight up in the air and maintain your constant speed? So pause the video here and think about these three options, and then resume once you've chosen one. Okay, so let's think about these three options. Once the ball leaves your hand, the ball will be traveling with parabolic motion, which means the ball maintains a constant velocity in the x direction, and in the y direction goes up and then comes back down. So what about these three options? So if you throw the ball at an angle of 45 degrees and maintain speed, what will the ball's velocity in the x direction be? Well, it would have the speed that you initially had as you were running. So let's say you were running at, I don't know, maybe 8 miles per hour. So if you're running at 8 miles per hour and you throw the ball is going to have a horizontal velocity of 8 miles per hour plus the component of its velocity that you throw it with in the x direction. So you would add that component of the velocity with which you throw it in the x direction to your speed. So now the ball is moving faster than you are, and so it will get ahead of you. You won't be able to catch it. So A probably would not be a good option. What if you throw the ball straight up in the air and slow down? Well, initially the ball would have your speed, say the 8 miles per hour. You throw the ball straight up in the air and then you slow down. Well, now the ball continues to move forward at 8 miles per hour, but you slow down. So now you're not matching the ball's speed in the horizontal direction, and you won't be able to catch it either, unless you have very long arms or don't throw the ball very high. So the best option would be to throw the ball straight up and maintain speed, because the ball will have in the horizontal direction the speed with which you were running, and then both you and the ball will continue to travel in that direction with that same speed. Because in the horizontal direction, the velocity of a projectile never changes. It only changes in the vertical direction, where it's influenced by gravity. So in this last slide, you can see a demonstration that we actually do in class, or it's a video of this demonstration. So in this demonstration, there is a cart, and the cart has a little spring cannon in it, and it shoots a ball bearing up into the air. So you give the cart some initial velocity. So this is like you running, holding the ball. And you can see that in order for the cannon to catch the ball when it comes back down, it shoots the ball straight into the air. So the ball leaves the cannon with the same horizontal velocity as the cannon, and then when it comes back down, the cannon and the ball's speed match each other, so they travel the same distance in the horizontal direction, and the cannon can catch the ball when it comes back down. So these are the big ideas that we covered in this day of class. We talked about freefall, which is the motion of an object in the y direction when it's only being acted on by gravity. So if you throw a ball, the instant it leaves your hand, it's only being acted upon by gravity, and so its acceleration in the y direction is minus g, or minus 9.8 meters per second squared. We also discussed projectile motion, which is a special case of two-dimensional motion, and saw that in the x direction, in the horizontal direction, we have constant velocity that continues throughout the motion, and in the y direction we have free fall. So you can use any of the free fall equations in the y direction as long as you remember your initial velocity. You just want to use the y component of the initial velocity. And so those were the big things that we discussed during this class period. During the next class, we will continue to look at some projectile motion examples, and we'll also start considering relative motion.